Okay, so new topic today. We're going to talk about Gauss's divergence theorem. This is one of the biggest theorems that we're going to talk about in the course. It has a tremendous number of applications in physics, and very powerful applications in physics. There's really a lot of cool stuff that happens in physics connected to Gauss's divergence theorem. So a lot of y'all are engineers, and so this is going to be a big deal for y'all. Anyway, but a quick reminder where this comes from. It comes from sort of ripping off the ideas that we've been developing this whole time in Chapter 15, right? So with the fundamental theorem of calculus, we looked at it from a certain point of view, found that we could apply that same idea in a different context, and now we have the fundamental theorem of line integrals, and then really opening our minds and applying it in a really superficially different but fundamentally kind of analogous way, we get Green's theorem. And of course, the big distinguishing feature of the Green's theorem application is that we're doing it really dimensionally different, right? Instead of a curve, one-dimensional thing with endpoints, zero-dimensional boundary, Green's theorem applies when you have a two-dimensional region in the plane with a one-dimensional boundary, right? It's one up dimensionally in all senses. Okay, so we're going to do it again. And let me just remind you what the pattern is. The pattern is that there's something that's computed on the boundary. With the fundamental theorem of calculus, we were looking at change, f of b minus f of a. That's computed on the boundary, right? Likewise, fundamental theorem of line integrals. With Green's theorem, it was circulation, right? Circulation, if you give me a two-dimensional region, circulation around the boundary, well, okay, from y'all's perspective, around the boundary, right, is computed on the boundary. You do a line integral around that boundary of that region. So, something computed on the boundary, which, though, actually accumulates over the interior. Even though cosmetic, at a glance, it doesn't look like an accumulating quantity. Mass is my favorite example of an accumulating quantity, right? If you're interested in the mass of a thing, if you chop it up into a bunch of little pieces, some of those little masses is, of course, the total mass, right? So, mass is obviously accumulating. It's not clear that these boundary computations are accumulating quantities, but they were. Change accumulates, thus giving us these two theorems. Circulation accumulates over the two-dimensional interior. Right? So thus Green's theorem. Okay, so that's the first feature. There's something computed on the boundary that actually accumulates over the interior. First observation. The second thing we needed is that on each little piece, when you're looking at total quantity is a sum of a bunch of little quantities. On each little piece, that I can relate that quantity, whatever it is, this accumulating quantity, to being some sort of a density times the size of that corresponding piece. All right, and this gave rise to these when we were talking about the fundamental theorem of calculus, we reinterpreted the derivative as being change density, which is a weird point of view and seemingly unnecessarily clunky point of view on the derivative, right? But it fits, right? And that gives rise to a very nice point of view when you're looking at Green's theorem. What is Green's operator? Most fundamentally, it's not we don't have pre-existing points of view like we did with the derivative. So what is Green's operator? What does it look like physically, geometrically? It's circulation density. It just represents this circulation that you're observing on the boundary. Okay, well, yeah, what's actually happening in the interior? It's coming from the interior. What you measure on the boundary is just the symptom that you see on the superficially, right? But it's coming from the interior, and Green's operator is telling you how much per unit size, how much of that circulation is coming from a general vicinity of that. Okay, all right. So, be on the lookout, right? We're going to be looking for this accumulation feature happening as we develop Gauss's divergence theorem. And then at the end, we're going to find that there is a corresponding notion of density. Okay. Alrighty. So here's our context. Three-dimensional setting. We're going to be looking at again, one dimension up. Not a one-dimensional curve with a zero-dimensional boundary. Not a two-dimensional region, right? Ooh, two-dimensional. Now this is a three-dimensional, a solid three-dimensional region with a two-dimensional boundary surface. Right, so yet another dimensional sort of step up. Okay. By the way, a couple of reminders. Don't forget this notation. I forgot to mention that when we first started using it. But for reasons that I won't spend any time on, but are kind of plausible, the partial derivative symbol is pretty commonly used to represent boundary. It's just a notational shorthand. Okay. Also, don't forget, when you talk about the boundary, when you say boundary of a solid, yes, that defines a surface, but that surface is oriented. Right? And the rule is always outward oriented. When you say the word boundary of a solid, that corresponding surface is outward oriented. It could have been inward, right? But the convention, standard convention, is to choose outward oriented. Okay, all right. So with this having been chosen, we're looking for three-dimensional solids with two-dimensional boundary surfaces. What is the accumulating quantity? Let me rephrase that. What is the quantity that, fingers crossed, we hope will be accumulating quantity so that we can proceed down this little road? Flux. Outward-oriented boundary flux. So, it seems like an arbitrary choice, and I suppose it kind of is. Sort of an arbitrary choice. Why do we make this choice? Why are we going to look at accumulation of, attempted accumulation of boundary flux? And the simple answer is, well, because it works. Because there's a theorem down this road. If we study this quantity, it actually does accumulate. There really is an associated notion of density. We therefore do get a result that we can put a box around and apply wherever it might come up. Right? And, if you can come up with some other accumulating quantity that's, computed on the boundary, but in fact can be demonstrated to accumulate over the interior, cool. Make your own theorem, right? There's nothing sort of exclusionary about this. We're studying this one because it's going to work. Okay, is everybody on board with the setup and the context? All right. So here we go. Boundary flux. It's perfectly obvious that this is computed on the boundary. It's right there in the name. Boundary flux. Okay. All right. By the way, a physical observation I want to make as we go on, before we go on here. So, reminder, we have this interior here. And we have a boundary then, so that's our solid three-dimensional region in R3. The boundary surface, just the surface right now, so it's hard to draw surfaces. So there's my surface. Surfaces come oriented. The orientation is the outward orientation. Now let's remind ourselves then, what does flux represent? Flux says we've got some vector field representing a fluid. Here's our fluid flowing. Right, and it's kind of flowing through this solid. Flux is measuring, let's see how many color choice here. Flux is measuring to what extent is the fluid flowing through the surface in the direction that the normal vector is pointing, right? And the observation I want to make here is that the normal vector, by pointing outward, what that means is we're measuring how much fluid is flowing out of the solid through the boundary surface, right? So when we say outward-oriented boundary flux, that means we're looking for how much fluid is leaving the region. So this is positive. You can see, because at least the way I have it drawn there, the green vector dot the purple vector, that's an acute angle, so it's a positive dot product. So we're going to get a positive flux there, and in fact the fluid is flowing outward. Whereas here, let's see, I need another normal vector over here. Right, in this general area of the boundary, the fluid is flowing inward. Right now, the flow vector, the fluid flow vector, the green vector, is making an obtuse angle with the normal vector. Dot product's negative. So inward means we have a negative outward flow. Right? So the grand total flux then is going to be, well, there's going to be some positive flux over there, and there's some negative flux over here, but grand total boundary flux is the sum, over the entire surface of those fluxes. Okay, so observation then, what we're talking about is, so this outward-oriented boundary flux represents how much of this fluid is leaving the region. Right, so flux says quantity per unit time of fluid. And if we're looking at quantity per unit time exiting the region, then we're looking at total fluid per unit time that's going out of the region. So anyway, just an observation about what we're talking about. Okay, back to our program over here. We've agreed that we have this boundary flux is sort of clearly computed on the boundary. It's right there in the name. Does it accumulate? Does outward-oriented boundary flux accumulate? Well, we're just going to have to draw the picture and think about it. And the answer is yes. And it's, by the way, I hope this picture conjures images, memories in your mind of kind of an analogous picture that we drew when we were talking about Green's theorem. Right? We talked about accumulation of circulation. And I drew, one little region and then another little region next to it. And then we talked about the union of those two regions, and we talked about the circulations around the various different boundaries and do they add up or not. It's morally kind of the same here. So we've got, on the one hand, we have this solid region here, R1. Right, and then we've got this other solid region, R2, over here. And we're interested in, if I were to compute the outward-oriented boundary flux for R1 and the outward-oriented boundary flux for R2, would I get, in adding those up, the total outward-oriented boundary flux through their union, R? Everybody see what we're talking about? Okay, well, so let's take an algebraic point of view on this first. By the way, just to be able to have things that I can talk about, I'm going to talk about this shared surface there. By the way, I'm just going to arbitrarily orient it that way. It doesn't matter. Really, in the big scheme of things. So I'm going to call that surface S3, the one that's sort of between the two of them. We can talk about flux through S3 as it arises, which it will. And then here's S1, and here is S2, oriented as indicated. Again, arbitrary how I do those orientations. Okay, but with all this set up, now let's talk about, well, what specifically is the boundary of R1? Here's our R1. What is the boundary of that thing? The boundary of R1 consists of, well, let's see here. There's that, which is S1, right? And then there's this thing, which, by the way, as part of the boundary of R1, is oriented outward, always outward. That's the rule. There's R1, outward is to the right. And hey, lo and behold, look at that. That is, in fact, the same way that S3 is oriented. And so the boundary of R1 is S1 plus S3. Is everybody happy with that? Okay. All right. Now, etc. For these other regions, let's talk about for R2, for this region. Well, part of the boundary of R2 is that, which is S2. right? Oriented in the same way that S2 is oriented, because outward from R2 points that way. Hey, that's the same way S3 points, so there you go. But wait a second, now be careful with this next one. The other piece of the boundary of R2 is that. Now, outward from R2, again, the word boundary means outward, right? So when we talk about the boundary of R2, well, we don't get S3, right? S3 is oriented in the way that little n vector is pointing. We've got S3, but oriented the other way. Right, so we get the opposite, 2 seconds, opposite, and so because of that, yeah, I'm going to put S3 here, but because of this issue with the orientation vectors, it's negative S3. Yeah?
So how do you know which way is outward for S3?
Well, no, it's the question of which way is outward for R2. Right, so the rule is if you have a solid, and if you want to talk about the boundary of that solid, then yeah, surface, right? But outward away from the solid, right? So since we're looking at this solid, we're looking at R2 as our solid. Outward away from that solid is that way. Does that make sense?
Yeah.
Okay. Cool. Okay. All right. Okay. So. And then a relatively easy one to consider is this. The whole thing itself, R. Its boundary consists of, well, there's S1 and there's S2. Both outward and therefore both in the arbitrarily chosen orientations of S1 and S2. Okay, so now just add them up. Do these accumulate the way they're supposed to? Is this plus this equal to this? And we make that decision by looking at the corresponding integrals. Is this plus that equal to this? And answer yes, because these cancel because of the minus sign. Right? We have this, here, let me zoom in for better visibility. Oh, I hit the wrong button. I'm sorry. Hang on a second. Here we go. Oh, too zoomy. There we go. So, flux through S3, you'll see appears twice in these summations, but with opposite signs. We've got a plus and a minus. Therefore, these cancel. Right? And with these terms canceling, that plus that is equal to that. And so this outward-oriented boundary flux accumulates. Now, again, just as a reminder, I drew this page very deliberately to look an awful lot like the analogous argument that we made for Green's theorem. So I think it's a really healthy exercise. Just flip back in the notes to when we were doing Green's theorem. And what you'll notice is it's sure, this is 3-dimensional instead of 2-dimensional. This has got boundary surfaces instead of boundary curves, right? But it's, other than the dimensional difference, there's a lot in common between these two calculations. Most specifically, the shared piece of boundary comes with two opposite orientations. That way is part of the boundary of that one. That way is part of the boundary of that one. And because of those opposite orientations, we get the cancellation. Yeah. Okay. All right. Okay, so back to our little program here. We have something that's computed over the boundary, and yes, it does accumulate over the interior, and this is a weird thing to get accustomed to, right? And the idea that boundary flux, if you're looking at the flux through the boundary, that it's very visibly measured on the boundary. And if you want to know fluid leaving a surface, you notice that at the boundary where it is in process of leaving the surface. And we're making the assertion here that even though it's computed on the boundary, you can think of that as, well, look, there's little boundary fluxes that are happening at all these little small little pieces that we chop up the solid into, And that really you're just adding up a bunch of outward-oriented boundary fluxes on little pieces all throughout the interior. Okay. All right. And we're going to come back and talk about that more in a few minutes. So here's our next step. Since we can chop it up any way we want, let's take our original solid and chop it up into a bunch of, increasingly fine little chunks. Right? It's an accumulating quantity, so outward-oriented boundary flux over the whole thing is the sum of the outward-oriented boundary fluxes on each of the little pieces. That's just the accumulation that we observed on the previous page. This, therefore, is a constant. That's independent of how you slice. So if you take a limit of a constant, it's same thing, right? Limit of a constant is that constant. And so what we've done is we've written total boundary flux now as a limiting summation of boundary fluxes on little pieces. And you can see this is already starting to look like an integral, right? This is, that's a lot of what a Riemann sum over a solid looks like. The only thing we're kind of missing, it would seem, is, the dV. So I need to put a delta V over here and divide by a delta V there. If only that, was something I could do, and that would make sense. Now we've really got a triple integral, right? So that's what triple integrals look like. The looming question is this thing on the inside, in the limit, of course. Is that a thing? And if so, is it something we can compute? Right, so as we chop finer and finer, as we're looking at smaller and smaller little pieces, is it true that the boundary flux on these little pieces per unit volume approaches some conveniently computable limit? Everybody see how that's the sort of the next question? Again, going back to our program here, we've got a boundary computation that does accumulate. We want to know, is there an associated density? So the answer to that question is yes. This thing that we'd like to know the limit of, that thing is something we can compute. And here's where I'm going to sweep details under the rug. This is just details. I don't think it's something that in Math 212 you need to worry about. So we're just going to assert what the answer to this thing is, this new integrand for our new integral, and here's the formula. As it turns out, y'all may recognize that thing. This is something that the book mentioned and gave a name to and a notation to back in section 15.1, completely sans context or motivation, right? They just said, hey, here's a formula, let's give this a name. And now you can see where it comes from now. Right, so this thing is called divergence. That's, you might say, the first notation for this, divergence of a vector field. Again, here's the formula. Okay, and then we talked about this very common notation to represent divergence with del dot. That's just because del, thought of as an operator, if you then kind of reinterpret it as a vector and play make-believe, pretend that you can do a dot product with a vector field, then in fact you get this exact formula. You can even see it kind of happening right here. There's your sort of del is made up of, this stuff. That's del. And F has components P, Q, and R, and this is how a dot product is constructed. So it's really very plausible notation. For whatever it's worth, by the way, this notation in my undergraduate physics courses, I saw this notation far more than I saw this notation here. Div. I don't know. It's just a little bit easier to write, I guess. And there's some mathematical reasons why it's convenient as well. But we won't be talking about those. Okay. So divergence F, sometimes called del dot F, just for the notational reasons. Okay. And before we spike the football on this new theorem, I just want to talk a little bit about terminology as well. I mean, let's not forget where this thing comes from. Let me circle the whole thing. So this thing called divergence, computed with that formula, represented with this notation. Why do we care about that thing? We care about it because it is accumulating quantity per unit size. It's quantity per unit size. It's a density. It's very much a density, right? We have this accumulating quantity of outward-oriented boundary flux that I have highlighted in blue. It accumulates just like mass does, right? You take a solid chunk of whatever and you chop it into little pieces. You add up the masses of the little pieces, you get the total mass. Likewise with flux, if you take a solid through which there's a vector field, if you look at the outward-oriented boundary flux on the solid, if you look at the outward-oriented boundary flux on the little pieces, if you add them up, you get the same thing. It's just like mass in that sense. So we have a quantity per unit volume. That's a density. So in the same way that we call, we use the term mass density when you're looking at mass per unit volume. Well, here we're looking at, I mean, I guess you would say it's outward-oriented boundary flux per unit volume, right? So, but it's just clunky to say outward-oriented boundary flux density, right? So people just call it flux density, and that's it's admittedly a little sloppy to call it flux density. So you've got to remember for yourself that this flux right here, when they say when they say flux here, they're talking about outward-oriented boundary flux. But what everybody says day in and day out is flux density. Okay. All right. Almost ready to put the finishing touches on the theorem. But just, again, another quick cultural note. The term divergence and the term flux density. Honestly, in my physics days, I heard the term flux density substantially more often. So this is really, in fact, why I pushed real hard long ago on the ideas of, and you know, it seemed weird when I decided, well, let's rename derivative. Let's call it change density, right? That seemed weird at the time, and I know it did, right? You don't have to, you know. So it seemed like a weird choice, and okay, yeah, sure, but it helps give perspective on how these theorems are developing. But the more you can get accustomed to the idea of the derivative, thinking of it as, you know, change per unit size, thinking of it as change density. Likewise, the more you can get accustomed to thinking of Green's operator as being circulation density, that's kind of been a sort of an on-ramp to getting you used to the idea of thinking of divergence as flux density. Change density is something, to my knowledge, I made up. You won't hear that anywhere else, right? Circulation density is a term that's used out there here and there, but I don't know, probably not as much. Flux density is super, super common. And in some contexts, they won't even use the word divergence. They'll just say flux density. It's just, that's what we're talking about. That's how we're interested in interpreting this. And divergence is just, I don't know, what's the point of that word? Right. So anyway, heads up. Okay, so now let's put the finishing touches on the theorem. Flux accumulates. Outward-oriented boundary flux, of course, but flux accumulates. Flux has an associated density that allows you to write this as a triple integral, and that density is computed with this formula called divergence. And there's our theorem. That's Gauss's divergence theorem. Okay, so I think it's very, very, very instructive and helpful to see how this is morally just fundamental theorem of calculus in the context of a three-dimensional solid with a two-dimensional boundary surface. It's really the same concepts. Right? Okay. Notational alternatives. Again, by the way, you notice how this page looks an awful lot like an analogous page that we had when we were talking about Green's theorem. Again, that's on purpose. I'm trying to emphasize all the analogies between these various theorems. Okay. So alternate notations. We use capital Phi to represent flux. So you might write it like that, right? Divergence, you can write with del dot, or you can write it with div, whichever, whatever, same thing. So sometimes you might see Gauss's divergence theorem written like that, and sometimes you might see it written like that, and of course sometimes you might see that or that, right? So be aware of the different options you might see. Yeah.
How is boundary flux like different than the net flux going through a solid?
Well, so they're the same thing, and I think if you were to, so let's think it through carefully, right? So flux through a solid. What do you mean by flux through a solid? All we have a definition of is flux through a surface. So when you say flux through a solid, I think what you mean is that solid has a surface, and we're talking about the flux that's going through its surface. So it in fact really is the same thing. Now people will sometimes say flux through a solid. That's another kind of terminological sort of slang, right? When you say flux through a solid, well, but they're the boundary of the solid, of course, right? That's the only thing that makes sense, yeah. So same exact thing. Is that cool? Does that make sense?
Yeah, I was about to ask, like, typically if there's like flux through a surface, let's just say.
Yeah.
Like, I know a lot of the times it's zero because like,
sure.
There's a
sometimes. Yep.
So like, would this end up, like, how would this not end up equaling zero?
Oh, yeah, sure. I mean, so here's, I'll just draw a quick picture here. Maybe we have our surface is a ball, like that. So we have a solid ball, and then the boundary surface is this sphere, right? And outward-oriented boundary. Maybe our fluid field looks like this. Yeah. So like maybe this is the flow of a fluid like air, and a bomb went off inside of there, right? And so so there's this positive flux, right? It's outward everywhere. That's how bombs work. And so positive flux, right?
Right.
Now you may be thinking about fluids like water. Water is fundamentally a different thing. That I'm aware, you can't spontaneously generate water. There's no water bomb that we could. Phoenix would love to hear about that, right? Right. So if water flows in, well, it's pretty much got to flow out, right? Because it's incompressible, right? So we're going to talk about that a little bit as well. And so in a case like this, and maybe this is where your intuition was, in a case like that, yeah, the boundary flux has to be zero.
Okay.
Right. Absolutely. So different kinds of fluids, different kinds of stories. Yeah. Okay. All right, so we are going to do an application in a couple of minutes. Y'all may recall I drew these diagrams, or I put up these diagrams on the board. It would take me forever to draw that diagram again, right? So, anyway, we saw this diagram previously, and I just want to remind you, just sort of a different point of view on what we've been talking about. The whole point of this is that we're taking some of the same ideas that we applied previously for the fundamental theorem of calculus, fundamental theorem of line integrals, etc., and just applying them in a different context. So the result is a theorem that's surprisingly analogous to those other theorems. And I want to just show you how this diagram illustrates how that works in comparison to fundamental theorem of line integrals. By the way, we have not yet gotten to talking about curl yet, so, well, here, I just scratched out too much. Let's not worry about any of this stuff here. Just ignore. We'll come to that soon. Next week, I think. Okay, but we've talked about in the fundamental theorem of line integrals that, by the way, don't forget, we've magically chosen to compose grad curl div in that order. Right? Okay, and we've got these kinds of calculations we've been doing, and here's how it reduces down to the for the fundamental theorem of calculus. If you take a function and look at its gradient field, if you take a curve and look at its boundary points, then an evaluation of the original function at the boundary points, an evaluation of the line integral of the gradient field on the original curve, you get the same thing. Okay, Gauss's divergence theorem. Let's just look again. Here's our Gauss's divergence theorem. Let's think through what this is saying. Notice the flux is being done on the boundary surface. The triple integral is of the divergence of the original field. And just tracing it through, what this says is, if you have a vector field and you compute its divergence, if you have a solid and you compute its, or look at its boundary surface, then the flux of the original vector field through that boundary surface versus a triple integral of the divergence over the original solid, which again I like to abbreviate, so that versus that, same thing. So it's extremely not only did we derive this in an analogous way, but we get an extremely analogous result. Okay. All right. Okay, so let's get our hands dirty and actually compute one. Here's a vector field. Here's a surface, inward-oriented sphere centered at the origin, radius 3. Okay, so we've got a surface, specifically an oriented surface. We've got a vector field that maybe is representing the flow of a fluid. Reasonable question, how do you compute the flux? Now, there's a brute force way to do this problem. The brute force way is to, do what we did kind of last time, right? Parameterize the surface, take that vector field, compute, take the surface, parameterize the surface, xu, xv, take the cross product to get in, pull back the vector field, plug in, f dot in, du, dv. We have formulas for this, right? So you can brute force it. And it's going to be kind of annoying and tedious. Let me emphasize what's going to be worst about this. The worst thing about doing this brute force is we're looking at a sphere. How are you going to parameterize a sphere? It's not a graph. Okay, so you're going to have to use spherical coordinates to parameterize it. That means that when you parameterize that sphere, x, y, and z are sines and cosines all over the place. Okay, so that means that's a bunch of sines and cosines. That's a bunch of sines and cosines. You're going to have sines and cosines cubed, right? It's going to be annoying, right? It's doable. You could do it, but oh man, what a headache that's going to be, right? Okay, so let's, plan B. See if we can get clever about this. Notice we have our brand new theorem here. Brand new theorem says if you're interested in computing a flux, hey, you might be able to rewrite that as a triple integral. And who knows, maybe that triple integral will be easier to calculate with. No promises. It's something you can try, though. So possibly. However, if you want to convert... that's too clunky. Let me do this. If you want to convert a flux into a triple integral, notice that this does not apply to just any old flux. This only applies to special fluxes. This specifically it says it right here. It's got to be the boundary of a solid. Your surface through which you're interested in your flux has to be the boundary of a solid. And again, not for kind of formal, uptight reasons. Right? It's got to be the boundary of a solid because I need to know what that solid is. That solid is the boundary of my triple integral. If your surface is not the boundary of a solid, triple integral over what? Right? The whole thing is complete crash and burn. It makes no sense at all unless your surface is a boundary of something. Yeah? Okay. All right, so we got to go back over here before we get a little too into the idea of using Gauss's divergence theorem. Is our surface a boundary? Okay, now let's see here. We have sphere, center at the origin, radius 3. Is that a boundary? There's a temptation to say, sure, yeah, look at that. It's all closed up and everything, right? That's the boundary of a ball. The problem is our surface is inward oriented. So our given surface is not technically a boundary of that ball, right? The boundary of the ball is outward oriented. Well, okay, no problem. The boundary of the ball then is just the opposite orientation on this surface we're actually interested in. Right? So yeah. Mm-hmm.
Why again do you know that the ball boundary is
Because that's an arbitrary convention. That's very standard convention. Just because when you talk about a surface, an oriented surface, you got to pick one, right? So the convention that's been made long ago and that planet Earth is on board with, so we're going to do this, is that the word boundary, as stated, means outward oriented. Yep, it's just a convention. And if someone had made a decision 150 years ago that the word boundary shall henceforth mean inward oriented, then we would have a totally acceptable math that would work that way, and it would affect other conventions in other ways. And but you could imagine that if we make contact with some civilization on another planet and we start comparing our notes in our multivariable calculus books, they might have done it the other way, and there's nothing really wrong with that, and then we'll have a problem. We'll deal with that when we get to it, right? But on planet Earth right now, it's outward oriented. It's just arbitrary. It's a great question, but it's just a convention is the answer. Yeah. Okay, so so the boundary. So and again, if we look at this solid here, right, the boundary of that solid is the outward-oriented surface. We're interested in the inward-oriented surface. The difference is a minus sign, and so the difference between those two orientations is that minus sign, namely that minus sign. And with that established, well, okay, so. This thing that I want to know, that integral, that flux, is that triple integral. There's Gauss's divergence theorem. Outward-oriented boundary flux, specifically boundary, outward-oriented boundary flux is triple integral of divergence over the interior. Everybody on board? Okay. So, and of course, don't forget to carry down this minus sign because of the orientation. Okay. Right. Okay. So now, what's the divergence? Well, the divergence is an easy calculation. That's just kind of a little bit of algebra. No big deal. Oh gosh, let me just get rid of. I don't need that anymore. Recover a bunch of my colors here. Divergence. 2 plus x. Just take the x partial of that, plus the y partial of that, plus the z partial of that, add it up, and you get that the divergence is 2 plus x. Everybody on board with that? Again, that's just partial derivatives. Everybody happy? Okay, now, what have we accomplished? We were interested in computing an integral that was looking like it was going to be kind of a nightmare. And what have we recovered? Well, we have a different integral. Now, have we magically solved the problem? No. We've translated the question that was looking awkward into a different question. And it's a dice roll as to, is this an improvement? Or did we just make it much, much worse? Could go either way. Right, and in this case, it's going to turn out to that obviously I picked my first example to be one that's going to work out nicely, right? I'm trying to pitch the theorem. I'm not going to start with one where it's a failure, right? But it works out very nicely. Now, how you compute this integral, it is very helpful to be clever with this, and specifically, while this is not a constant. And it's not symmetric over any planes that B is symmetric over. Okay? So there's a temptation to say, well, I can't use any of my tricks. But if you turn this into these two integrals, then lucky break. This integrand is constant, and I get an easy evaluation. Right? The volume of the ball is a long since known geometry formula. This integral is 0 by symmetry. Gotta love it, right? Now, make sure you got to document at least a little bit. You've got to tell me what is the plane that you're declaring symmetry through, right? And you have to correctly observe that the function has odd symmetry, and you've got to correctly observe that the domain is symmetric through that plane, right? And then you can just declare it equal to 0. By the way, you might have noticed I'm relaxing the rule a little bit now, right? The rule used to be, back when, before exam 2, the rule was that you had to furthermore write down the formula for the reflection and then directly confirm that the integrand does indeed have the odd symmetry, directly confirming by plugging in the reflection. So now that that's been on a test, I'm going to declare that, okay, we know how that works. And so now, a little bit easier, slightly relaxed rules on declaring symmetry. You still got to give me something, right? If I let you do what I got away with in college, I know the scam, right? So no sort of Hail Marys equals 0 by symmetry. I hope I'm right? So you got to tell me what is the plane, and you have to correctly note, and you have to be right. The symmetries, the two required symmetries. Okay, all right. So anyway, the point is, this is easy, that's easy, and so this divergence theorems really helped us out. We turned what would have been a really hard problem into a, hey, not that bad, worked out pretty well problem. Everybody on board? Okay. Let's see here. So I want to talk about interpretations a little bit, and so let's talk about fluids. We're not going to get to the incompressible stuff today, but here's kind of our first interpretation of boundary flux. So remember, we're talking about boundary flux here. That's not just an arbitrary flux through, some random surface. It's got to be the boundary of a solid. And boundaries point outward from the region. Flux represents how much stuff is passing through that surface. And so the punchline is, flux represents, in total, how much stuff, what's the rate that stuff is flowing out of this region? Total quantity of stuff per unit time. And so that's what we have here. Flux represents the rate at which stuff is leaving the region. And the K is just in there because I don't want to deal with units. Right? So that's just whatever. It's a constant. Don't worry about it. Okay. Y'all can worry about that when you're in engineering classes and physics classes. Okay, so what I want to do with this, though, is make this sort of immediate physical interpretation of flux. And what does this tell us about divergence? Right? Okay. All right. Well, divergence is flux per unit volume. So, roughly speaking, if I apply this formula to some little small piece of solid on the inside of the solid, and then just divide by volume, right? Flux per unit volume gives me divergence, wherever my little piece is. Mass per unit volume is density. And what that means is, it gives us a very nice interpretation of divergence. If we're talking about a vector field that represents the flow of a fluid, divergence, and by the way, there's certain assumptions that are going into this, and we'll talk about those assumptions next time, but just in the simple context we're interpreting here, divergence is telling you how fast density is changing negatively. So this is telling you how fast is density going down. It's the rate of change of density of stuff. Right? And so now I've got a picture that I want to show you all, and I'm going to spend more time on this picture next time as well. But I want to make a little bit of discussion of, let's just go straight to this part. We'll talk about these in a minute. On Friday. So here's a picture of what's going on with Gauss's divergence theorem. We've got a fluid, right, that's flowing, as indicated by these horizontal arrows. We have this region. Now, forgive me, I drew the picture two-dimensionally. Of course, it's really three-dimensional. It's just harder to draw a three-dimensional picture, right? So if you want to make this three-dimensional, I mean, just, you can visualize like this, right? But let's just draw it two-dimensionally. We have outward orientations. So this is what we mean by the direction, the appropriate direction through these surfaces. And let's think about flux. Right, the flux through this boundary, well, as the fluid flows, there's no fluid flowing through this boundary. It's flowing along that curve. Well, surface. It's flowing along that boundary, not through that boundary. So there's no flux there. Likewise, there's no flux down here. Right? There's negative flux through that part of the boundary. There's positive flux through that part of the boundary. Right? Grand total is actually positive because these little field vectors here are short. There's not a lot of stuff flowing in there. So there's a little bit of negative flux on that part of the boundary. There's a lot of flux on this part of the boundary. Right, so grand total positive flux. Okay, positive flux means we have stuff is leaving this region. However much stuff there was in there, it's running out faster than it's running in. Right? So what's happening to the grand total amount of stuff in this region? We're having a decrease in stuff in this region. And what we're seeing there is this. The flux that you measure by looking at the boundary is telling you how fast the amount of stuff is changing. Right? You have this mass exodus of stuff happening. Okay. All right. So So let's talk about densities, though. How fast is the density of stuff changing in this region right there, this little small area? Well, there's just as much stuff going out as there is going in. The density in this little region is not changing at all. Right? I mean, just imagine if this was, a stampede of people. There's just as many people running into your little zone than there are going out of the zone, right? Whereas over here, right, there's a lot of exit. There's a lot of stuff leaving that region, a lot of people departing that region. And there's a few people going in, I suppose, right? Not very many people going in. Grand total then, how's your density changing in this region? In that region, there's more stuff going out than there's stuff going in. Density of stuff in that area is going down. And that's what this is telling us. Right? So the divergence is a way of measuring how fast is the density changing in any particular area. Okay, more to say about this next time. See y'all later. Have a great Wednesday. Oh, and hey, I have homeworks to return if you'll stick around for just a